Hello everyone, welcome to the next module. The focus of this module is to continue with data flow. If you remember in the last video, we had defined what is data flow in a graph, what was definition of a data, what was use of data, and how to track a data from its definition to use. And we saw an example of how this is used. So what we will see today is definitions of criteria that are based on data flow, data depths and data uses. And I'll also tell you briefly about how to define or work on algorithms that will help us to achieve these data flow coverage criteria. Data flow coverage criteria algorithms is a very vast area. Early papers came out in the early 80s and there's still active research going on. I will not be able to cover all the algorithms that deal with data flow coverage criteria. What I'll point to you at the end of this lecture would be some links to good reference material where you could read up more to get to know what algorithms related to data flow. So just to recap what we did till now, we are at the module where graphs are our models that we use to model software artifacts. We saw structural coverage criteria over graphs. Then we looked at basic algorithms over graphs, algorithms for defining test requirements and test paths for structural coverage criteria. Then I moved on to defining data flow in graphs. Today what we will be seeing is data flow coverage criteria. How is data flow coverage criteria defined? Data flow coverage criteria is basically defined as a set of DU paths, D for definition, U for use. What is a DU path? If you remember from the last lecture, a DU path is a path corresponding to a variable that is given as a parameter to a path that begins at a definition of a variable and goes all the way till the use of the variable. Intermediate in this path from its definition to its use, we insist that the variable doesn't get defined once again. So the path is definition clear for this variable, right? So what is DU path? It's a path from a definition of a variable to a use of a variable, such that at every intermediate node in the path, there is no further definition of the variables, right? What we will do is we'll group various kinds of DU paths to be able to define data flow criteria. What these criteria will basically check is they'll basically check how a definition of a variable reaches its use, right? How are we going to group DU paths? We are going to group DU paths in two different ways. The first grouping that we will discuss is as per their definitions. The next grouping that we will discuss is as per their definition and use. So how are we going to group DU paths as per definition? So when we group a DU path according to a definition, we consider DU paths with respect to a given variable defined in a given node. And we define it like this. So V is the variable that whose definition and use we are tracking. It so happens that V is defined at this vertex Ni in the graph. So what is a def path set called DU of the variable V at the node Ni? It's the set of all DU paths with respect to the variable V that start at the node Ni. What is a def path set? A def path set at a node Ni for a variable V is the set of all DU paths that begin at that node Ni for that variable V. Please note that the number of such def paths for a large program, fairly reasonable sized program, can be very large, but we still have to find them and work on them to be able to define data flow coverage criteria. It is also worth noting at this stage that while we group a DU path with respect to a place where it begins to get defined, we don't really group it with reference to its uses. So it turns out that in literature, grouping it with reference to its uses is not considered to be very essential and it's not useful for testing. The other kind of grouping that we will do is per definition and use. So such a grouping is what is called a def pair set. So we have, as usual, fixed a variable V. The definition of that variable begins at Ni and its use happens with reference to this node Nj. Right? So what is a def pair set? A def pair set is a set of DU paths for a variable V that's fixed, which begin at node Ni and end at node Nj. Right? So a def pair set collects together all ways to get from a definition of a variable which is at node Ni to its use which is at node Nj. Please remember when we talk about DU paths, we had insisted in the last lecture that such paths be simple. So DU paths are always simple. So a def pair set is a collection of such simple paths. A def pair set could also be defined to begin at node ni, in which case it's the union of all the def path sets for that definition. That is, if we say a def path set begins at node ni for a variable v, then we consider all the different uses at which it can end and take their union, and then we say that it's a def pair set. So just to recap, what are we going to do? We are going to define data flow coverage criteria by grouping together DU paths. We group together DU paths in two different ways. The first grouping is as per the definition. We say for a variable v, we collect all DU paths that begin at node ni. That is, the def for variable v is at node ni. So that is called a def path set. The next grouping is as per definition and use. So for a given fixed variable v, we consider all the beginning at a variable ni and all the ending or use at node nj. That's called a def pair set. It's a collection of pairs ni, nj such that v is defined at ni and used at nj. So you remember last time we had looked at the small pattern matching example. It searches for a pattern occurrence in a subject. Actually, I would like to mention here that there was a small error in the control flow graph that I had shown you last time. This edge from vertex 10 was drawn to meet at vertex 4 in the control flow graph that I had shown you last time. That's slightly different from the way it occurs in the code. It should actually be like this. This edge at vertex 10 should actually go and meet at vertex 3. This is where the while loop begins. So this is the corrected CFG. Please consider this CFG to understand the example. So if you remember, we had first drawn the CFG. I had given you labels with all the statements, and I'd taken the same CFG and annotated the graph with definitions and uses. So that's what this graph is. I have put the same graph with this small correction done. So what I'll do is we will understand how the various DU paths look like. For simplicity, I have taken this variable I sub. That's the variable that I fix. There is a definition of this variable I sub at node 10. If you see here, I sub definition at 10, variable I sub is defined. What is I sub? If you remember in the code, it's an index that runs over the subject, right? And tries to pattern match every character in the subject with the corresponding character in the pattern, right? So here is a definition of I sub. So I can group this definition of I sub in two different ways. At node 10, I can group it with reference to all its uses at node 10, or I can group it with reference to its definition at node 10 and use at each of the other nodes where it is used. If you see, it is used in this particular node, it is used in this particular edge, it is used in this particular node, it is also used in this particular edge from 7.8 to 7.9. So there are several places, right? So if I try to trace the def path sets and the DU path sets, so here are the DU path sets for I sub at node 10. So from 10, I can go back through this edge to 3 and then to 4, right? That's what this trace is here. And then from 10 to 3 to 4 to 5. So 10 to 3 to 4 to 5, and then I can do 4 to 5, 5 to 6, 7 to 8 or 7 to 9. Both of them have I sub in them. That's what these two sets paths do. 10, 3, 4, 5, 6, 7, 8, 10, 3, 4, 5, 6, 7, 9 and so on, right? So basically what I'm saying here is that you fix this variable I sub, you begin its definition at 10 and look at all the places where it's used. It's used in this edge, it's used in this edge, it's used in this edge. So trace paths in the graph that begin its definition at 10 and end in one of its uses, take all their union, that's this set. Alternatively, I can say I begin its definition at 10 and consider its use at 4, in which case I get only this path. Then I say I begin its definition at 10 and consider its use only at 5. I get this path beginning at 10, ending at 5. Similarly, from beginning at 10, ending at 8 is this path. Beginning at 10, ending at 9 is this path, and so on, right? So if I take the union of all these things which begin at 10 and end at various vertices, I get this set, right? So this is how I define def path set and def pair set for a variable at a particular node and in the control flow graph. Now we are ready to define data flow coverage criteria. So like structural coverage criteria, if you remember while we had defined structural coverage criteria, I had told you that sometimes structural coverage criteria can get to be infeasible because sometimes certain kinds of loop might insist that a path be traversed at least once. So we do test paths to trace coverage criteria by taking side trips and detours. That's what we will do here. We say a test path P is set to detour a subpath D as long as it tours the subpath D and the subpath that it tours is definition free for that variable. Remember, the only thing that we insist is that once it's defined at a particular node, it reaches its use at another node. It could be through a direct test path or it could be through a test path with a side trip or a detour. Irrespective of whether I take a side trip or a detour, I insist that that side trip or detour also be definition clear. That's what this is. And it says you can freely use side trips and detours whenever you want to get test paths to satisfy coverage criteria. This is exactly like we did for structural coverage criteria. Now, what are the three kinds of data flow coverage criteria that we are going to look at? These are the three TRs for the three different data flow coverage criteria that we are going to look at. The first coverage criteria says that each definition should reach at least one use. The second coverage criteria says that each definition should reach all possible uses. The third coverage criteria says that each definition reaches all possible uses. Not only does it reach all possible uses, it reaches all possible uses using all possible different paths that you can trace out in the graph, right? So as I told you, these are just the test requirements. Whenever you need to get test paths to satisfy these test requirements, you can assume what is called best effort touring. Best effort touring basically says that feel free to allow side trips and detours if you want to make these test requirements feasible. So here are the definitions of the coverage criteria. What does all defs coverage say? It says that for each definition of a variable v at a node n, the test requirement contains at least one path that reaches a use, right? All uses coverage says that for a variable v that is defined at a node ni, I reach one path which basically reaches all the uses for every pair of def at ni and use at nj. So to repeat, what is all uses coverage? Fix a variable v. Variable v is defined at ni and used at nj. And this is for every possible use of the variable v. So nj varies over different uses of the variable v. And my test requirement says you cover every possible path that takes the variable v from its definition at ni to its use at nj, right? The third one says all du paths coverage. It says for each def pair set ni njv, tr contains every path d in s. If you find these definitions cumbersome, the easiest way to understand data flow criteria is to look at the previous slide. So it says there's one criteria which says every def reaches at least one use. That is all defs coverage. I don't worry about covering all the uses, but I want to cover every definition. The second one, all uses coverage, says every definition reaches all possible uses. So that's why it's called all uses coverage. The third definition, all du path coverage, says that for every definition and every possible use of it, take different paths, every possible path that goes from a definition to a use. Right? Is it clear? So basically three different elementary data flow criteria. Cover every definition, make sure it reaches at least one use. The second says cover every definition, make sure it reaches all its uses. The third says cover every definition, make sure it reaches all its uses using every possible different path to get to the uses. Right? So you remember this small example that we had seen in the last lecture. There were only two variables in this small graph, x and z. X was defined here and used at 5 and 6. Z was defined at nodes 5 and 6. So suppose I have to cover all defs criteria for x, then the test path that I would take is this 1, 2, 4. I could either take 6, 7 or 5, 7. Basically what I want to say is that x is defined at node 1. Take a test path that covers this definition and one use. It could cover either this use at 5 or it could cover this use at 6. The example test path that we have given covers the definition at 1 and the use at 6. The second criteria, all uses for X, basically says X is defined here and used in two different places in the graph, at node 5 and at node 6. So the two different test paths that I should take are 1, 2, 4, 5, 7, which covers the use at 5, and 1, 2, 4, 6, 7, which covers the use at 6. Of course, I could take these two test paths by going through node 3. That is also the same, that will equally well meet the test requirement. In this particular case, I have just taken the two test paths that go through node 2. The third condition says from the definition of X at node 1 to its uses at nodes 5 and 6, you not only cover this definition to all its uses, you consider all the paths that take you from this definition to this use. So if you see, there are 4 different possible paths. I could do this 1, 2, 4, 5, 7, or I could do 1, 3, 4, 5, 7. That will cover the definition of X at node 1 to its use at node 5, right? 2 different ways. Similarly, if I consider the definition of X at node 1 and its use at node 6, there are 2 different paths again, 1, 2, 4, 6, 7, and 1, 3, 4, 6, 7. That's what I have listed here, right? Is it clear? So just to repeat, all def says go from every definition to at least one use. All uses says go from every definition to every use. All DU path says go from every definition to every use, taking every possible different path to do this. These are the 3 elementary graph coverage criteria that we will see. Now I want to spend some time trying to make you understand how these coverage criteria are related to each other. So if you remember, when we looked at structural coverage criteria, we had seen all these coverage criteria, and this was the picture that gave how each coverage criteria subsumes the other, right? Node coverage, edge coverage subsumes node coverage, edge pair coverage subsumes edge coverage, prime path coverage subsumes all 3, and so on, right? Now we want to be able to add data flow criteria to this picture and understand how the 3 data flow criteria that we defined subsume each other and how are they related to the structural coverage criteria. So as far as data flow coverage criteria is concerned, before we look at subsumption, I would like to make some elementary assumptions. These are not strong assumptions. They're basically true for every program that we expect to be compiled and working fine. So the assumptions that we are making are every use is preceded by a definition. Otherwise, you'll understand, right? If there is a use that for a variable that is not defined, then compiler will throw an error, right? If the variable is not declared. So it's not a big restricting assumption. This is true of all programs that are syntactically sound and compilable. The second assumption that we make is that every definition reaches at least one use. This may not be found by a compiler, but elementary static program analysis tools will be able to find this. It basically says that there are no variables that are defined and never used in the program. So every variable that is defined is used at some place in the program. The third assumption says that when I have a node in the graph which has branches or multiple outgoing edges, at least one variable should be used on each of the out edge, and we assume that the same variables are used on each out edge. What it says is that even if different variables are used, you consider the set by considering the union of all the variables. So under these assumptions, we are ready to look at data flow coverage criteria subsumption. So what are the subsumption thing? So there are 3 criteria, if you remember. What are the 3 criteria? All defs coverage, all uses coverage, all DU paths coverage. Because all uses says from every def you go to every possible use, it's reasonably straightforward to see that all uses coverage subsume all definitions coverage. In turn, all DU paths coverage says you not only reach every def to every possible use, you figure out all possible ways of going from the def to use, right? So it by default subsumes all uses coverage. So that's what is given here. It says that if we satisfy all uses criteria, by our definition, we would have ensured that every definition was used. So it subsumes all defs criteria. Again, if we satisfy all DU paths criteria, we would have ensured that every definition reaches every possible use. So it subsumes all uses. So the picture for data flow coverage criteria subsumption looks somewhat like this. All DU path coverage subsumes all uses coverage, which in turn subsumes all defs coverage. So this is exclusively for data flow coverage criteria. This diagram is exclusively for structural coverage criteria, but both deal with graphs. So I would be able to want to reach a stage such that I can relate one to the other. That's what we are going to do. Our goal is to understand such a picture. So if you see, this is two of the subsumption criteria figures merged into one. On this left hand side that I'm tracing out here through my mouse, this part, which begins at complete path coverage, prime path coverage, goes on to this edge, pair, edge, and node, and these round trip coverage criteria was purely related to structural coverage criteria. These three were the data flow coverage criteria subsumption that we saw now. What have I done now? I have put this extra arrow here and then this extra arrow here. So I have come up with two extra subsumption relation. First one says that prime paths subsume all DU paths. The second one says all uses subsume edge coverage. These two are the only two new subsumption relations that I have put. The rest were all explained earlier. Why do these two additional new ones hold? They hold because of the following reason. You remember each edge in the graph is based on the satisfaction of some predicate. That was one of the assumptions that we made, right? So each edge has at least one use, and because of this, when I cover all uses, I definitely cover all edges. So all uses subsumes edge coverage, this arrow. Because every DU path is a simple path, prime path coverage subsumes all DU paths, because prime paths are simple paths that are not subpaths of any other path. So prime path coverage subsumes all DU paths. This is, of course, a small point to be noted here is that this subsumption is with reference to only feasible test criteria. But for now, we can safely assume that this holds for most of the programs that we will look at, right? Now that we've seen data flow coverage criteria and how the subsumption works, and this is the overall picture for graph coverage criteria, I would like to spend some time looking or discussing algorithms for data flow coverage criteria. So when I do data flow coverage, this is the overall flow chart of the process for data flow coverage. So I begin with my input program. I do some kind of a data flow analysis on that program. For this, you could use any ready-made static program analysis tool available, or you could write your own elementary data flow analysis tool. And then using some kind of data flow analysis, I pull out the def use pair sets, right? Once I have a DU pair, my goal is to be able to define some coverage criteria and generate test data for that coverage criteria. If I finish achieving my coverage criteria, I'm ready with my test cases. Otherwise, maybe the coverage criteria that I defined was infeasible. I go back, pull out another DU pair, and attempt all over again to work with a new coverage criteria that would again be feasible or infeasible, right? So this part, data flow analysis, is not in the scope of this course. So I will leave you to read this on your own. Feel free to pick up any basic books related to the first few chapters of compilers, or use some elementary static program analysis tools to be able to do this. We will try to do a brief discussion on what are the algorithms for this part. It so happens that for test data generation, there are so many different algorithms. You can do algorithms based on explicit search, based on random search, based on symbolic execution, based on model checking. Several different techniques and about 4 decades of research has gone into algorithms in these areas. I will not spend time looking at these various algorithms because we'd like to move on looking at other test case definition terminologies. But what I would like you to point out is this good survey that has come out very recently, dated April 2017, available as one of the ACM computing surveys. That's an exhaustive survey on data flow testing techniques, and you will be able to find reference to papers that use all these approaches for test data generation in this survey. Most of the data flow testing criteria that we discussed in this paper has been borrowed by these two papers of Vayukar and her student Raps. So these two are very classical papers for data flow testing techniques. As you see, they are dated early 80s and quite exhaustively referred to. The material that I have presented is basically derived from these two papers and the textbook on software testing by Amman and Ofu. In the next module, we will model graphs, source code for as graphs, and we'll see how the various structure coverage criteria that we saw till now can be used to test code. And then we'll look at design and requirements. And by next week, I hope to finish the module on graph-based testing. Thank you.